So next up, we have Dr. Stachel. He's also from the University of Alberta, and he's going to be talking to us about the kinds of fluids and melts that can form these diamonds. Thank you, Thomas.
Thank you, Karen. Unfortunately, Graham has the only pair of these glasses where you can see down, and we also have the problem that we can't simply look in the window of the reactor like Daniel showed us and observe. Too late now. So we have to work mainly with deducing from other lines of evidence how diamonds form, and that's what I want to talk to you about today. So what is our standard model that is widely accepted? So over the last, say, about 30 years, the view emerged that diamonds are a metasomatic mineral. What that means in geology is that the diamond was subsequently introduced to a rock, and that the rock, when that happened, remained in the solid state, or at least largely in the solid state. And two end members of reactions that could make diamonds were proposed. The first one is that we have a fluid or melt that is more on the oxidizing side. It contains carbonate. This carbonate enters a rock that is more reducing, and so we can have a diamond-forming reaction where this carbonate is converted to diamond. And the role that the substrate has is that it has to consume the oxygen that is liberated there by oxidizing iron from the Fe2 plus to the Fe3 plus state. And the other end member reaction is exactly the opposite. Here, the lithosphere is the oxidizing part, and we have deep mantle fluids ascending that are methane-rich. They react with this more oxidized lithosphere that is then an oxygen donor, and we can make diamond and water. Unfortunately, we have no direct observation, so we can't really make an a priori choice what is the right deduction here. But we have learned from that it's obviously not enough that we think about diamond stability in terms of pressure and temperature, but that we have to consider this third intensive parameter, oxygen fugacity. And I'm sure, like myself, you are not that familiar with oxygen fugacity. It's one of the most horrible parameters in geochemistry. So in the next slide, I give you everything you need to know about it for this talk. So we express it usually as a log difference to a buffer reaction. Which buffer that is of no interest to us for this talk. The good thing of the buffer that I chose here is simply it sets the most important rock on Earth's surface to zero. Mid-ocean rich basalt covers 2/3 of Earth's surface, so the FMQ buffer is essentially equivalent to that rock type. So if we go now to plus values, then we are log units more oxidizing than mid-ocean rich basalts. If you go to the negative side, we are more reducing. And here we hit this first reaction that we discussed. This is the conversion of carbonate into diamond, about 1.5 log units more reducing than mid-ocean rich basalt. And then when things get seriously reducing, so now we are almost 5 log units more reducing than mid-ocean rich basalt, then we have the conversion of iron oxides to metal iron, featured in the talk on the type 2 diamonds. So this would be called the IW buffer. So remember these two reactions, and then we can move forward, and you don't really need to know much more about oxygen fugacity. So using these parameters now, let's map out the diamond stability fields. So we have pressure here converted into depths, and together with depths, we go along a cratonic geotherm temperature increases as well. So we hit the graphite diamond transition at around 150 kilometers depth here. Then we said, okay, if we are on this side of this buffer reaction, carbonate will be stable, so we don't get diamond, although we are on the right pressure field. But if we cross this EMOD buffer, then we have diamond stable. And then we have a second reaction. This was our iron oxide to iron reaction, the IW buffer. And it is generally assumed that this is the lower end of diamond stability in redox space, simply because the carbon then dissolves in the metal and is not available to make diamonds. So if we draw out a diamond stability field, it would be this yellow field here. Okay, and then we discussed first I want to show you where upper mantle would fall here. So this is an average value of what we assume upper mantle is upper mantle would contain about 3.6% of all its iron in the ferric iron state, as Fe3+, and then we can calculate what the redox state should be, and we get a curve like that. So when we are in the diamond stability field, normal upper mantle, also from its redox properties, should actually be diamond stable. So that's looking good. So now let's discuss our proposed diamond forming reactions. So if we want to use carbonate, it can't come from the lithospheric mantle itself. We have to bring it in externally, say through the process of subduction that was discussed in previous talks. So we bring carbonate down in the mantle, and then it could interact here with our average mantle. That is much more reducing, and that looks okay with the discussion, with the reaction that we had proposed. And we can discuss the same for methane-rich fluids that could come from the deep mantle, from below the figure. If they interact with this average mantle, then this average mantle is more oxidizing, so we could convert some of the methane to diamond plus water. But does it really happen? And the principal question we have to answer here is what really is the redox buffering potential of this lithospheric mantle? Does it really have the iron that can be converted either way to buffer these diamond forming fluids that enter? So what I will calculate in the next slide is that we simply take mantle at one of the end member compositions, say we sit here at the EMOD buffer, and then we add methane till we bring the mantle over there, or the opposite way around. That gives us a measure of what the buffering capacity of the mantle is. So here, this is all the oxygen that is required to pull our mantle across the entire diamond stable field in terms of redox. And then we did this for a whole bunch of samples, but I want to draw your eye only to these 4 samples down here. These are xenoliths from the Finch mine in South Africa. And what this modal garnet percent actually measures here is the depletion of the rock type. And diamond source rocks are, in general, very depleted rock types. So these 4 rocks have the signature of typical diamond source rocks. And now let's look at how much oxygen we need to pull them across the entire diamond stable region. And it is 50 ppm of oxygen. That's all that is required to pull these rocks across the diamond stable region. So if we convert that in terms of fluid, then that means we only have to add 25 ppm of methane or 70 ppm of CO2, and we have pulled these rocks from metal stability to carbonate stability or the other way around. You can express that as you just have to breathe at them, and they will be completely changed in their redox properties. People who model mantle metasomatism, that is the influx of fluids in mantle rocks, usually work with about a weight percent of fluid interacting with these rocks. So we are then about 3 orders of magnitude higher than what we actually need to completely convert these rocks. So the conclusion is the fluids really rule, and the mantle rocks can only follow. So diamond formation through buffering by mantle rocks will not happen, or it will be incredibly inefficient. So let's think again, what can we do then? We obviously need a process where the mantle rocks are not the drivers. In this diagram here, we have the key components that form mantle fluids: carbon, hydrogen, and oxygen. And we have the 3 principal fluid species that would exist in such fluids: methane, water, and CO2. Then I plotted our buffer reactions in here. So this is the carbonate stability buffer. So here we have carbonate, below we have diamond, and up here we have diamond. And here's this buffer where metal stability begins up here. So our diamond stable region is here, around the water maximum. Okay, then with the blue lines, I simply connected the fluid phases, and then the red lines are calculated points where we actually would start the precipitation of diamond. So when you go across this blue line, you don't immediately get diamond. You have to actually cross the red line, and then diamond precipitation would start from the fluid. This is for one condition. If you now vary the pressure and the temperature, then you would see, if you had extremely good glasses, that this red line starts to move around a little bit. Since we don't have the really good glasses, we now enlarge this section here. So I will now plot the carbon content versus a ratio that depicts this axis here. And you will immediately recognize the water maximum again in the next slide. So that's our water maximum. That's the ratio that depicts essentially the oxygen to hydrogen ratio, and we plot the mole percent of carbon in the fluid. And we do cooling of the fluid by 200 degrees centigrade. And you see at the water maximum, the maximum amount of carbon in the fluid decreases by 0.8 mole percent. That means we precipitate 0.8 mole percent of diamond from this fluid during cooling. How can that now suddenly work? Before we said we need redox reactions to precipitate diamond, and now the fluid does it all by itself. Seems somewhat strange, but how it works can be understood if we look at the speciation of fluids. So here we have the various, the mole fractions of the various fluid components, and again our oxygen fugacity. And this was our average Mantle value here for one particular condition, 5 GPa, so 150 kilometers about. And this purple line essentially crosses exactly where we have the maximum water content. So a typical fluid at these conditions would have 98% water, but you see it also crosses where we have both species, CH4 and CO2, present in the fluid. And the purple shade is essentially a 1 sigma ratio of natural samples around that. So natural samples seem to sit exactly where we are at the water maximum and have both methane and CO2 present in the fluid. So that now gives us a way to make diamond, because we can simply react these two species in a redox neutral reaction. We don't need any wall rock anymore. The CO2 reacts with the CH4 and we make diamond plus water. That we have now a reaction doesn't mean that this is really what is happening. Is it efficient enough? Does it really make enough diamond? So let's calculate that out. So let's assume we work with 200 degrees centigrade cooling. We said we precipitate 0.8 mole percent. That would be half of 8% of diamond. Diamondiferous xenoliths from the papers that exist contain about 5 to 550 carats per ton. So that would be the grams per ton. So this is the diamond content that we want to be able to generate. What we would need to do that is the interaction of 200 grams to 22 kilograms of fluid per ton of rock. That really isn't that much. If we express that as percent, then we are easily in the range that the people who work on introduction of certain trace elements through mantle metasomatism assume. Yeah? So it's no problem to generate the required trace element contents. How would we envisage that geologically? There is a particular species of minerals that are transported by kimberlites that are called megacrysts, and the people that work on megacrysts tell us that they precipitate in one place over temperature gradients of over 200 degrees centigrade, which means there are very hot intrusions that slowly cool down. So the delta T is at least 200 degrees centigrade. And as soon as these intrusions begin to cool and crystallize, they will release fluid in the adjacent mantle wall rock. This fluid progresses into this cooler wall rock and will start to precipitate diamond. And by the time we have our whole intrusion being crystallized and cooled down to ambient temperature, we have created a halo of diamond around this intrusion, which with the exact size depending on a whole bunch of parameters. There is one more way how we could do that. It's that we don't just have cooling of a fluid, but that we have ascent of a fluid along a geothermal gradient. If I calculate that out for a reasonable range of redox values and we let it go through the entire diamond stable region in the lithosphere, then we find this doesn't really work particularly well. The initial value looks very good. This is about twice as much as we did during our cooling process, but we precipitate these diamonds through the entire lithosphere section. So what I precipitate per meter of lithosphere is a very small number. Remind you again, this is what our xenoliths contain. So to make that amount of diamond, I would need to interact 1 ton of rock with 2.5 to 275 tons of fluid. And that's an unreasonable assumption to have way more fluid than we have rock. That doesn't make sense. So that's obviously not the process how we make diamond. And we focus on cooling. Okay, for the last 3-4 slides of the talk, I want to try to link what I've told you now to what is essentially Oded Navon's life work. He has spent 30, 40 years studying the uglier part of diamonds. So these are the fibrous or fluid inclusion-rich parts of diamonds, where he has zoomed in on these micro-inclusions and analyzed their chemistry. And over these 30 to 40 years of work, his group has defined 4 end members of inclusions that occur within these diamonds. They are all hydrous, but they have different other chemical components. So there are saline brines, there are potassic brines, then they grade into carbonatitic hydrous inclusions. They can be either calcic or magnesium rich, and that then grades into fluid inclusions that again are hydrous but can contain silicon and aluminum. Take away from that slide that essentially all these inclusions contain some amount of carbonate. So why don't I model with what Oded really finds in diamonds? The problem simply is that I can't. We don't have the thermodynamic data to do that. The most sophisticated model to work with mantle fluids is the Zhang and Duan model, and you can only model pure CHO fluids. So it's essentially a modeling problem, but when you take these pure CHO fluids and you put them into an experimental capsule and you bring that capsule to the pressure temperature conditions of diamond formation, then you have at the minimum 10% dissolved solids and often up to 30 to 50% dissolved solids in these fluids. So at mantle conditions, at diamond conditions, these CHO fluids have to be high density fluids. And essentially the Navon group and we talk about the same thing, just from different angles of examination. So the last thing I have to resolve for you is this. I said that these fluid inclusions typically contain carbonate. So you could now make the argument and say, okay, then the diamond reaction always has to go along this EMOD buffer reaction because that's the only place where we have carbonate in equilibrium with diamond. But there was a breakthrough paper by Stachel and Frost where they showed that this reaction is actually only true in the solid state. In the solid state, we would be confined to this red line, whereas as soon as the carbonate is contained in fluids or melts, how far we can go in redox space depends on the concentration. So an XCO2 of 50 means it's a 100% carbonate, and there in the diamond stable region we essentially agree with the green dashed line in the EMOD buffer that's more or less the same. But as soon as we start to dilute, that's 20% carbonate, 2% carbonate, and 2 per mil of carbonate, we can go to extremely reducing conditions. We said the diamond formation typically occurs around the water maximum. If I interpolate here, I can easily have fluids with 30% carbonate stable in that redox space here. And then we can rewrite our diamond forming reaction. Instead of using CO2, we just use CO3 here. So we have carbonate reacting with the methane in the fluid to make diamond plus water. And the role that the country rock takes here, or that the mantle peridotite takes here, is that someone has to accept the MgO that comes out of here, but we don't need a redox partner, right? It's still a redox neutral diamond forming reaction, we just have to get rid of the MgO. So what I would like you to take along from that talk is this: redox buffering by mantle rocks likely not possible. They simply aren't strong enough from their buffering capacities. So diamonds precipitate then by cooling of CHO fluids. It's an efficient process. It creates the right amount of diamond. And at high pressure and temperature, these CHO fluids actually are high density fluids. So Oded Navon's work and our work can easily be reconciled. Thank you very much.
Does anyone have any questions? Go ahead.
Thomas, nice talk. And the cooling model to precipitate reduced carbon is a nice model. You can also drive the equilibria at a constant temperature to precipitate reduced carbon if you mix fluids, one that's oxidized and one that's reduced. And I'm just wondering what the disadvantages of such a model are.
I think that over. Yes, that would definitely work too, but what you would then, you wouldn't really need very extreme redox end members in the two fluids. And that doesn't seem to fit with this very narrow band of FO2 conditions that we see that the mantle rocks show us, because from that way of thinking, what the mantle rocks show us is what the fluids are, right? The redox state of mantle rocks is imposed by the fluids they interacted with. So to mix an oxidizing and a reducing fluid, we should really also see mantle rocks that reflect these two fluids passing through, and everything seems to fall in a narrow band that always overlaps with the water maximum. So the mantle fluids don't seem to be very variable, and this also fits with the carbon isotope composition of diamonds.
It does depend how far apart you make the two fluids. They could be extremes, and then you would only need 2% as much fluid because you wouldn't need to have all the water. But if they were close in FO2, but on other sides of the cusp in the COH diagram, they could be well within the uncertainty of FO2 measurements.
Yes.
Yeah.
It's possible, absolutely.
No, Reese first.
Sorry, I didn't see that.
There are a lot of discussions of mantle metasomatism to enrich the hospital guide. And the fluid you talk about and this metasomatism fluid, are you referring to the same thing, or there could be entirely different fluids?
The fluid that we are talking about is one type of metasomatic fluid, or maybe even the type of metasomatic fluid. If it's the only one, I cannot prove that, but diamond formation seems to be always associated with a particular type of mantle metasomatism that is fluid-driven, with particular expressions in the rare earth patterns of the garnets and so forth.
So you think this fluid could carry all of this highly enriched nitrous element that make this change that happen in the garnet, Klein pyroxene in the mantle?
Yes. Yeah, because it is really a high-density fluid, as Oded would point out. So it contains all these dissolved solid components, and it's not just carbon, hydrogen, and oxygen. It's 10 to 30 to 50% something else.
Thank you.
Go ahead, Mark.
Do you think that reabsorption happens when the growth environment changes, or later in the history of the diamond when it's moved out of that environment?
What were the first two words?
When you get reabsorption of the diamond. Resorption.
Most of the resorption really happens in the kimberlites, but now and then it happens also in the mantle, and that would, for example, happen when a more oxidizing fluid passes through. Then you can have a phase where you damage your diamond. Yeah. But most of the resorption that we see, the formation of dodecahedral diamond crystals, occurs in the kimberlite.
Great, thank you very much.